Today we're going to be learning about confidence intervals. This is Chapter 7, Section 1, and specifically we're going to be calculating confidence intervals for means today when the population standard deviation, sigma, is given. A confidence interval is a form of inference where we are taking the sample mean and using it to calculate and predict what the population mean would be. We can do this for different confidence levels. We're going to be focusing on the three main confidence levels today, 90, 95, and 99, but you can calculate any confidence level confidence interval. The confidence interval is the range of values that is used to estimate the population mean, as well as an interpretation of those numbers. Here's a visual of what a confidence interval region looks like. So if you were asked to find the 95% confidence interval, we would place 95% in the middle of the normal distribution. That would leave 5% for both tails. Specifically, 2.5% would be left over on the left tail, and 2.5% would be left over on the right tail. We will be using those values to find what is called a critical value, which is where the shading begins. This on the left would be a negative critical value, and this on the right would be a positive critical value. Let's start there. So, our first common confidence level is 90%, and we are going to find the critical values that are associated with that confidence interval. So, if I put 90% in the middle of my distribution, so this is 90%, that would leave 10% for both tails, or 5% for the left tail and 5% for the right tail. I'm going to go ahead and find the value that is associated with 5% in this left tail region. So I have the negative chart here, and we are scanning the middle for the closest number to 0.05. So if I do that, I see 0.0505 right here and 0.0495. Notice that those two are evenly split. When we had an evenly split probability before, we averaged the two z-values together. So if I look, this first one is negative 1.64, and this second one is negative 1.65. If I average those two values together, I get a z-value of negative 1.645. This is the line that's on the left side. Since I also have a line on the right side, that would be a positive 1.65. So my critical values are positive or negative 1.645. That is going to be true anytime you calculate a 90% confidence interval. Okay, we're going to go through that process one more time, but this time for a 95% confidence interval. So on this one, I would put 95% in the middle of my distribution. That leaves 5% left over for both tails. So this left tail region is 2.5%. I'm going to scan the negative chart for the closest number that I could get to 0.025. If I look, I see that number exactly on the chart. The z-value that's associated with that is negative 1.96. So my critical values would be positive or negative 1.96. Okay, pause the video. See if you can find the critical value that's associated with 99%. Okay, so I went ahead and drew the distribution, put my 99% in the middle of the distribution. That leaves 1% left over for both tails. So each tail is going to be 0.5% or 0.005 as a decimal. I scan on the chart for the closest I can get to 0.005, and notice I have two identified, 0.0051 and 0.0049. It's another evenly split. So we're going to average the two z values together of negative 2.57 and 2.58. So my critical values for 99 is positive or negative 2.575. Okay, just to recap those guys, anytime you're asked for a 90% confidence interval, the critical value is going to be positive or negative 1.645. For 95% confidence, 1.96. And for 99% confidence, 2.575. Okay, the formula that we will use to find the entire confidence interval is x bar plus or minus the critical value, z alpha over 2, times the standard deviation over the square root of the sample size. Remember, x bar stands for the sample mean. The z alpha over 2 represents the critical values, those we just found in the previous slide. Sigma stands for the population standard deviation, and n stands for the sample size. So looking at our first example, it says a researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet F-150. A sample of 50 trucks had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6 days. Find the 95% confidence interval of the population mean. Okay, so let's pick out the important information from this prompt. The first number that I see is 50. That's talking about the sample size, so that's n. The next number that I see is 54. That's talking about the mean of those 50 trucks, so that's our sample mean, x bar. The next number is 6. That's talking about the population standard deviation, or sigma. We do want a 95% confidence interval, which in the previous slide, we found that critical value to be positive or negative 1.96. Okay, so if we look at our formula, x bar plus or minus the z critical value times the standard deviation over the square root of the sample size. I'm going to plug the numbers into this formula. My mean was 54 plus or minus our critical value is 1.96. Standard deviation is 6 over the square root of the sample size, which is 50. We're going to go ahead and do this math. So over here in my calculator, I am going to plug in Okay, I am plugging in 6 divided by the square root of 50. I'm going to multiply that by 1.96. So I'm going to be adding on and subtracting off 1.663 from 54. So if I take 54 minus that number, I get 52.337. And then I'm also going to take 54 and add on the 1.663. And that gives me 55.663. So that is my interval that I believe the population mean to be between. anytime you calculate a confidence interval, you must interpret the meaning of those numbers. So basically, we're going to be writing a sentence that sounds similar to this one for that last example. I am 95% confident that the true mean time it takes to sell an F-150 is between 52.336 and 55.663 days. Okay, the next example, it says a survey of 30 adults found that the mean age of a person's primary vehicle is 5.6 years. Assuming the standard deviation of the population is 0.8 year, find the 99% confidence interval of the population mean. Let's go ahead and identify the values in the prompt. The first number that I see is 5.6. This is talking about the mean age. So that's X bar. Oh, I missed the value of 30. That's talking about the sample size. So that's N. 0.8 is the population standard deviation, sigma. And a confidence level of 99% corresponds to the critical value of positive or negative 2.575. So if we plug the values into the formula, X bar 5.6 plus or minus the critical value 2.575 times the standard deviation 0.8 divided by the square root of the sample size 30. Okay, let's go ahead and calculate this on the calculator. So I'm going to do the standard deviation divided by the square root of the sample size first. I am then going to multiply that by the critical value. This gives me, just kidding, 0.8 divided by the square root of the sample size, multiplying that by the critical value, 2.575. I'm going to be adding on and subtracting off 0.376. So 5.6 minus that value. So 5.224. And I'm going to take 5.6 and add on the 0.376. So my two values I get are 5.224 to 5.976. Those are the values of my confidence interval, and to interpret it, I am 99% confident that the true mean age of a person's primary vehicle is between 5.224 and 5.976 years. All right, there's example 2, guys. All right, for example 3, what I would like you to do is pause this video and then resume it when you have an answer and we can check what you have. Okay. All right, here's the example all worked out. We had an N of 40, a mean X bar of 32, a standard deviation sigma of 2.3, and 90% corresponds to a critical value of 1.645. Plugging those values in, we have 32 plus or minus 1.645 times 2.3 over the square root of 40. On the calculator, we got 31.402 to 32.598. So I am 90% confident that the true mean time spent is between 31.402 and 32.598 minutes. Okay, guys, this concludes today's lesson. So go ahead and message me if you have any questions.